Let's take a look at an example problem for Module 10 for ME12 Dynamics course. So in this example problem here, we can see we have a given diagram, a pivot point here at A, pivot point at B, another pivot down here with a slider at D here. We can see the length from A to B is given to us as 0.4 meters. The length from B to D is 0.4 meters. The angle is 90 degrees between AB and BD. And we have the angle here between AB and the ground at 45 degrees and between BD and the ground at 45 degrees as well. You can also see that they tell us the slider is moving to the right at a velocity of 3 meters per second. So in our problem statement, they tell us that a linkage undergoing motion is shown. The velocity of block D is 3 meters per second. Now they want us to find our angular velocities of links AB and BD. So our general plan of attack for this problem here, we want to do is locate the instantaneous center of zero velocity of the link BD. So from the information from our given diagram and problem statement, our next step here is to create our setup page. So in the setup page, I have my example problem here given to me. I know that my VD, my velocity of D, is moving to the right at 3 meters per second. You can see that over here in my diagram. I redraw out my entire diagram in 2D, real simplified form here. See pivot at A, length of this member here, AB, of 0.4 meters. And then from B to D, we have a length of 0.4 meters as well. Angle initially between AB and BD is 90 degrees. Angle between AB and the ground is 45, and angle between BD and the ground is 45. Right there. Now they want us to find our omega AB, so for this member here, and our omega BD for this member over here. Now that we've had a chance to read through our problem statement, create our setup page, we have a place that we can go back to and reference all that information, what they're looking us to solve for, as we start our solution to the problem. Now the first thing we want to do when we start our solution to the problem is take a look at the second link BD here. So we have information that's given to us in the problem statement of this VD. So that's what gave me the indication that I really wanted to start with link BD first. So I redraw just my BD, have my velocity going over here to the right for VD. I have this rotating up as that moves to the right of my omega BD. And that's something I like to physically imagine myself moving the body. How do things rotate within the system? How do they move? Where do they translate? So from that there, I can see that my omega BD is rotating counterclockwise when my VD goes to the right. And I can see I have a velocity here at point B coming from member AB over there that's coming in at 90 degrees, so straight onto this here because AB and BD are at 90 degrees from each other at the beginning. So my VB is coming down here at 90 degrees right there. So I've set a little notation over here. We know the direction and locations of VB and VD. Again, VD because it's given the problem, and VB from where member AB is at 90 degrees to BD. So therefore, we can draw position RB relative to my IC and RD relative to my IC, and from that, find my IC, my instantaneous center of zero velocity. So I just wrote up a little summary here explaining exactly what I just showed in the diagram. Since D moves to the right, it causes link AB to rotate counterclockwise about point A. The instantaneous center of zero velocity for BD is located at the intersection of the line segments and drawn perpendicular to VB and VD. We also want to note that VB is perpendicular to link AB. Therefore, we can see that the IC is located along the extension of link AB. So using that information that we saw from the previous slide, what we want to do next is draw out the IC for this link BD. We're going to deal with each of these links separately. So we do that here. We come down, here's our link from B to D right there. We know its distance is 0.4 meters. So we can come straight up here and right off of this at 90 degrees. So if we come off at that 90 degrees there, we come straight up there, right there, we can see that this intersects right here. So this angle is going to be 45. This angle is going to be 90 degrees. This angle is going to be 45 right here. So we can do a little bit of trig, and we can say, okay, the tangent of 45 is opposite over adjacent. And from that there, we can back out our lengths from some basic trig for our RBIC and our DIC. So our BIC is right here from point B, and our DIC right here is from point D to our IC. So from that there, we find out then is our RBIC from here to here is equal to 0.4 times the tangent of 45 degrees. Do out the math there, and we find that our length here is going to be 0.4 meters. Now our RDIC over here is going to be equal to 0.4 divided by the cosine of 45 degrees, or is equal to 0.566 meters. So just some basic trig, sine, cosine, tangent, SOHCAHTOA, TOA, in order to back those out from a simple right triangle. So next thing we want to do is solve for our omega BD. So in order to do this, one thing that we want to do is recall a relationship that V is equal to omega R. So plug in our known values for this here. We're talking about V. This is our velocity at point D. And this is given to us in our problem statement. So we have a numerical value for VD. Now this is equal to our omega, is going to be our omega BD. And our R, in this case here, when we're dealing with length BD, is going to be our RD relative to our IC right there. We just solved for that value on the previous page. So now we can rearrange this and solve for our omega BD because we have a value for this. We were given a value for this. Our only unknown is our omega BD. So we can rearrange this, and omega BD is equal to our VD over our RDIC here. So we plug in our values here. So it's given to us 3 meters per second. We solve for this of 0.566 meters. Simple math there. We find out that this is equal to 5.3 radians per second moving counterclockwise. So again, magnitude and direction here. So this is moving counterclockwise by rotating there. This is our omega BD. Next, now that we've already looked at our length BD, we want to go back now and look at our length AB. So we now have our omega for BD. We have our velocities. So now we can go back and correspond that to length AB. So length AB, we redraw that out on its own over here. We can see A is fixed to the ground at this pivot point A right there. This is going to be rotating clockwise for omega AB, has a length of 0.4 meters, and our VB is perpendicular to point B at the end of length AB. So length AB is going to be subject to a rotation about point A down here where it's pinned. So we can recall V is equal to omega R. So V sub B is equal to our omega BD plus or times our R of B relative to our IC right there. So we can rearrange that in order to get our VB. So we plug into that value right there. And what we've done here is we take our omega AB is equal to this VB over our RA from V is equal to omega R again as well, and we can plug this relationship for VB directly in right here. So now our omega AB is equal to this relationship for VB divided by my RB relative to A. Plug this in here, RBIC times our omega BD divided by our RBA is equal to, well, we have numeric values for this. This we found to be 0.4 meters for our position of B relative to our IC, and we have our omega BD we'd already solved for as 5.3 radians per second, and we're given the length of AB of 0.4 meters. So everything we need to numerically get a value for omega AB is there. Plug it in, omega AB is equal to 5.3 radians per second, but now this is rotating clockwise. So one thing to note, as I solved this problem, I used these to notate which direction things were rotating in. Now, if I had chosen a standard Cartesian coordinate system with my y positive going up and my x positive going to the right, then using my right-hand rule, we could say that, okay, counterclockwise is positive and clockwise is negative according to my right-hand rule. So therefore, omega BD is equal to 5 radians per second, and omega AB is equal to negative 5 radians per second. Now, the reason I didn't do this is because I wanted to illustrate a point that your sign convention changes based upon what your chosen coordinate system is. So this really makes it crucial that when you choose your coordinate system, you label it and you stick with it, because it's going to affect your final answer. So if this is some problem that you guys have turned in for a homework or an exam question, and you didn't have this here, and all of a sudden I saw that there was the wrong signage in your final answer, I would have no way of understanding that, oh, you were using a different coordinate system than I anticipated. So 2 things to take away from that. 1, always draw out your coordinate system, clearly label it, make sure you stick with it. And 2, it doesn't hurt to, even if you have a coordinate system, add these to the end of your answers as well. So you come over here, okay, counterclockwise or clockwise for negative, counterclockwise for positive there. Just add those little arrows right to the end of your answers regardless of your sign.